Good morning, students. In the last class we have just started the topic D and F block elements, and in the last class I have given you introduction of D and F block elements, that is definition of D and F. What are D block elements? The elements containing groups 3 to 12 which lie between S block and P block are where the d orbital or n-1 or penultimate shell is partially filled are called as d block. And the 4f and 5f orbitals are being completely filled. In the next two groups, they are called as f block. And in the last class, I have also discussed about position of d block in the periodic table, and next electronic configuration, and what about the irregularities in the electronic configuration. Reasons for that we have studied in the last class. Now, in this class, we will study some of the properties, general properties of D block elements. So here these D block elements contain outermost n-1 d1 to 10 and ns orbitals are available for bonding. So see here, ns orbitals are available for bonding similar to s block, so that they are the representative elements and they are more metallic compared to S block elements. So here the properties of D block elements are explained based on metallic bond. First I will just explain what is meaning of metallic bonding, then what are the properties of D block elements, how they are explained. Here, see here, metallic bond is the bond where, so in the center metal atom is present with a positive charge, and this metal atom is called as kernels. Okay, metal atom which is having positive charge is called as kernels, and this metal positively charged metal atom is surrounded by sea of electrons, and these sea of electrons are called as mobile electrons or sea of electrons, and this model we are called as electron sea model. So there is electrostatic force of attraction between positively charged kernels and mobile electrons. So because of this force of attraction, attractive force of electrostatic force of attraction, so many properties of the D blocks can be explained. Okay, so metals have got some specific properties like metallic cluster, then malleability, ductility, okay, thermal and electrical conductivity, then fourth one or fifth one, hardness, then last property. So see here, metallic cluster means the shining which is created on the metallic surface. We know that every metal has got characteristic shining. Okay, and the shining, how it observed, just see here, when light falls on the metal surface, okay, the electrons on the surface of the metal will absorb some of the radiation. When light falls on the metal surface, then mobile electrons absorb some of the radiation and they transmit remaining radiation in the form of clusters, so that metallic cluster is observed by the D block elements. Then malleability means thin sheets of metals. See here, when the metal surface is hammered, okay, so metal drawn into thin sheets is called malleability and ductility. So here when we just hammer the metal or in between the metal atoms, so that we can form thin metal sheets of the elements. Okay, so that malleability, ductility means drawn into thin wires, same reason is there. So when metal surface is hammered, so the electrons present on the mobile electrons present on the upper layer will be slided in between the metal surface, so that we can have as much as thin wires possible. So that this is the explanation for ductility. Now thermal and electrical conductivity. So for thermal conductivity, thermal means heating. So if you heat the surface of the metal, okay, provide heat to the surface of the metal from one end, so that if heat is provided, then here the electrons will get kinetic energy, or the mobile electrons are having more kinetic energy, and they will pass to the next layer. Similarly, again the kinetic energy of the next layer increases, and they will transfer their energy to the higher level, so that the heat is transferred from one end of the metal surface to the another end of the surface. Thereby there will be thermal conductivity shown by the metal surfaces. Okay, so next one, electrical conductivity. When we apply the electric field, so positive and negative charges will be present, so that if you just apply the electrical field, electron starts moving from negative end and they will move towards the positive end, so that along with moving they carry the current through them, so that they conduct electricity. Now next property, tensile strength, high tensile strength. So this is also because of strength and hardness. These two properties are because of metallic bonding. So why the metallic bonding is caused here? See here, in this I have told you, in the d orbitals or d orbital electrons, metals are having n-1 d1 to 10 and ns1 to 2 electrons available for the bond. More the number of electrons available for bonding, more stronger will be the metallic bond, and hence metal will be having high tensile strength and it is considered as hard. Okay, so more the number of electrons available for bonding, then more will be the cause of, or more will be the metallic bonding caused by the metal, so that metal is having high tensile strength and hardness. Okay, now in detail we can consider the hardness property. So I have just told you that 1863 Kelvin, and in these metals Hg is a liquid having boiling point of 234 Kelvin. Okay, this is about the hardness caused by D block elements. Now next property, melting point and boiling point. Melting point and boiling point. Okay, next property, here your main properties start, melting point and boiling point. So I will draw a graph for the melting point and boiling point. Now before going for the melting point and boiling point, another property is that metallic structures. So metallic structures, here I already told you that these D block elements are more metallic compared to S block elements, representative elements. So there will be every element or every metal is having typical metallic structure. So like HCP, BCP or CCP. Okay, every metal is going to possess the metallic character like HCP, BCP or CCP, except zinc, except the metals like zinc, cadmium, mercury and manganese and technetium. All the other metals are having typical metallic structure. In the 3D series, the metallic structure is as follows: scandium, titanium, vanadium, chromium, manganese, Fe, cobalt, nickel, copper, zinc. These are the 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements of 3D series. The metallic character will be HCP, BCC. So about the metallic character, that is HCP, CCP and BCC, you have already studied in the solid state topic. Okay, so here BCC means body centered cubic lattice, HCP means hexagonal cubic packing lattice, like that. Titanium is also having HCP, then vanadium is having BCC, this is also BCC, then chromium is having BCC, CCP. Okay, then manganese is having the structure other than this, so that X is the other structure than these three. Then Fe is having BCC, HCP, then CCP, then CCP, then X. Okay, so except I have given you the example zinc, cadmium, mercury, manganese and technetium, all the other D block elements are having typical metallic structure, and that structure will be either SCP, BCP or CCP. In that, BCC means body center, HCP means hexagonal close packing, CCP means cubic close packing, like that. The packing, the structure is different. Now next one is melting point and boiling point of D block elements. So here there is a graph. This is atomic number. Along the x-axis we are plotting the atomic number, and along y-axis melting point into 10⁻³ Kelvin. Okay, so titanium, vanadium, chromium, manganese, then Fe, cobalt, nickel, then Cu. Okay, next. So zirconium, 4th group series, niobium, then molybdenum, technetium, then ruthenium, rhodium, then palladium, then Ag. Similarly, okay, So this is the trend: hafnium, tantalum, then tungsten, rhenium, osmium, iridium, then platinum, A. Okay, this is the just trend which is followed in the melting point or boiling point. What is meant by melting point or boiling point? So just you know the meaning of that. Okay, melting point of boiling point. Melting point means it is a conversion from solid to liquid state. Okay, melting point is a temperature at which solid completely dissolves or it just turns to liquid state. And boiling point is the temperature at which liquid is completely converted to gaseous. So, in order to convert from one state to another state, here both the processes will involve breaking of old bonds, and formation of new bonds. Okay, so boiling and melting and boiling, both the processes. In the process, solid is converted to liquid or liquid is converted to gas. In both the process, we are having solid state is converted into liquid. For that, what we have to do? Break the old bonds which are present in the solid, tightly held covalent bonds. Then in the liquid, bonds are loosely held. So that first break the bonds which are present in between the molecules, then form the new bonds which in between the molecules, so that there will be process of solid to liquid or liquid to gas takes place. So now in this melting and boiling process, so if the metal is having stronger metallic bond, what happens? Stronger metallic bond. What happens? Stronger metallic bond means metal is hard. Okay, harder or hardest in nature. So with the number of electrons, as the atomic number increases, number of unpaired electrons goes on increasing. You know that in the periodic table. Okay, I have given you the electronic configuration. In that electronic configuration, we have observed that as the atomic number increases along the x-axis, we are increasing the number of electrons available for bonding also increase. So as a result, with the increase of number of electrons, the hardness of the metals also goes on increasing. Okay, so strong metallic bonding, we have just told that in case of strong metallic bonding is there, then metal becomes harder in nature. So harder means they are held by strong bonds. Okay, so that strong bonds require more energy to be broken. More energy is required to break the strong bonds, so that melting point will be high. So melting point will be high. This is the consequence of melting point. With the strong metallic bonding, metal turns to be harder. Harder metals will have stronger bonds, and stronger bonds will require more energy to break the bonds, so that metals having melting point or boiling point high. So if you just observe the graphs, okay, general trend, what will be the graph here? So in the beginning, as the atomic number increases, so melting point increases, it reaches to a maximum where it is maximum in the middle of the series. Then again after the maximum, with the again increase of atomic number, it goes on decreasing. This is the trend generally observed for 3D, 4D and 5D elements. Okay, what is the trend? With the increase of atomic number, melting point increases because there will be increase in the number of electrons in each case. In each case, we are adding one electron number of unpaired electrons increases, so that melting point also goes on increasing. It reaches a maximum, and maximum in the middle of the series, there will be maximum number of unpaired electrons. So after the maximum, again with the increase of atomic number, melting point go on decreasing. Here we see the exceptions for the metals manganese, technetium and osmium, where instead of increasing, there will be decrease in the melting point. This is the exception for melting point and boiling point. So in the manganese, technetium and osmium, there will be increase. Instead of increase in the melting point, there will be decrease in the melting point because of some reasons. Okay, so this is about the melting point and boiling point of 3D, 4D and 5D series. So here melting point maximum in the middle indicates that there will be maximum number of unpaired electrons available for bonding, so that metals will be harder, and hard bonds or hard metals will be having stronger bonds, so that stronger bonds require more energy, and hence melting point or boiling point will be high. Okay. Now next property, enthalpy of atomization. Enthalpy of atomization, delta HA. Okay. Next property, enthalpy of atomization. Enthalpy of atomization. So this is represented by the letter delta HA. Okay. So it is measured in kilojoule units. So here also same graph is followed for delta HA, but with the change, instead of melting point along the y-axis, we are having the delta HA or enthalpy of atomization. This enthalpy of atomization is an important factor in deciding reactivity of the metal, so which is based on electrode potential. Okay, this is the letter I have written is for electrode potential. So what is the relation between electrode potential and reactivity and enthalpy of atomization? Let us see. Okay, if the metal is harder, why harder? Because of strong metallic bond. Okay, so enthalpy of atomization is Fe metal is converted to Fe atom. This is the one example. Okay, M metal is converted to M atom. In this process also, it involves breaking of the old bonds and formation of the new bonds. Enthalpy of atomization. Atomization means conversion of metal into its corresponding atom. That also is involved with breaking of old bonds and formation of new bonds. Okay, so that also require energy. So hard metals will have strong metallic bonding, so that what is the result? They will have higher melting point or boiling point. Correspondingly, they will have higher enthalpy of atomization. So here one relation is that in between reactivity and electrode potential, higher the enthalpy of atomization, okay, higher will be the or more positive will be the electrode potential. More positive will be the electrode potential, and hence less reactive will be the metal. Less reactive is also called by the name nobler. Okay, so relation between enthalpy of atomization, reactivity and electrode potential is like this. Higher the enthalpy of atomization, that metal, why higher the enthalpy of atomization? Because of these reasons: strong metallic bonding, hardness, melting point higher. So that with these all reasons, enthalpy of atomization is higher, so that more positive will be the electrode potential and less reactive or nobler will be the metal. So whereas lower the delta HA enthalpy of atomization, lower will be or negative will be electrode potential, so that metal becomes highly reactive. Okay. So now here I have drawn the graph. The same graph which we have used in the melting point is explained for the delta HA. So with the same explanation, okay, now the trend for 3D, 4D and 5D is in this way. 3D is having lesser enthalpy of atomization. So if you go for 4D, then 3D it will have more value than 3D. Then it will go for 5D, it will have more value than 5. Okay, it is because, so here 4D and 5D, the electrons are more tightly held or more closely packed because of close packing of 4D and 5D electrons. So the enthalpy of atomization of 4D and 5D is greater than that of 3D. Okay. So now in this class we have discussed some of the properties of D block elements. In the next class we will discuss the remaining properties of the D block elements.